we were looking at was wave interference. That's really the whole chapter is on interference. And we looked at stuff with waves in one dimension. Say I have one wave that comes like this, and I get another wave that's going back this way. I know that instead of bouncing off, what waves do is when two waves are in the same place, they add up linearly. And the nice thing about interference, just purely resonance patterns, you can do an awful lot of it just using pictures. You can do almost all of it. When you just get resonance, you deal with it in terms of just drawing pictures. The thing is there will be other stuff we have to look at, so it's nice to be able to do a little bit of the math. Once again, most of the stuff that I'm going to get right now, you're going to say, man, that's obvious, and that's okay. I want to look at adding these two waves, because when I do add these two waves, I know that when they hit one another, they're going to just add up linearly. So if I have two waves, and once again, I'm going to think of this as a nice sinusoidal wave, and this thing's a nice sinusoidal wave like that, I could think of it as adding two waves. This would be A times the sine of, well, the first one's going to be kx minus omega t, that's moving to the right. Going to drop the phase angle just to make the math a little bit easier to look at. When I get the wave moving back in the opposite direction, is A times the sine of kx plus omega t. And you would say, yeah, this wave is traveling to the left in the negative direction because of that plus sign. And I've said this a couple times, but to do almost all the trig you're ever going to have to do, all you really have to remember is that sine squared of x plus cosine squared of x is equal to 1. That'd be like, I think they call it your Pythagorean theory of trig. And then the angle addition formulas. The angle addition formulas, and I harp on this a lot because there's no way you're going to derive the angle addition formulas off the top of your head. I can't do it. It is a nasty. But once you know the angle addition formulas, you can do almost all the other junk you're ever going to have to do with trig. So it's really nice to know that the cosine, let me put this up here. The cosine of, let's say, x plus or minus y is going to be equal to cosine x, cosine y minus plus sine x, sine y. Okay, whatever sign I have here, I have the opposite sign here. And then with the sine function, which is what I'm just going to be using now, the sine of, say, a plus or minus b is going to be sine a cosine b plus or minus, same sign here as I have here, sine b cosine a. Like I said, man, it's really, 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 really nice to have those. Because deriving them is a pain in the neck. And the angle addition formula is just appear in a lot of different places. It's nice. This comes up a lot, so it's nice to be able to deal with that. So when I'm going to add these two, I get A times, it's going to be the sine of kx cosine of omega t minus the sine of omega t cosine of kx plus, this is going to be A times the sine of kx cosine of omega t plus the sine of omega t times cosine of kx. If I type the A through there, I get A sine of kx cosine of omega t minus A sine of omega t cosine of kx plus A sine of kx cosine of omega t plus A sine of omega t cosine of kx. And the thing is, if I look at it, I go, hey, this term and this term are the exact same thing, except one of them's plus and one of them's minus. So they're going to cancel each other out really, really nicely. And the other thing is, this and this are the exact same thing. So I can say when I add those two waves up, I get 2 times the amplitude of an individual wave times the sine of kx times cosine of omega t. A couple things to mention about this. If I look at it, this part purely depends on time. This part's purely depending on position. This part's the amplitude function. They will say the amplitude function is 2 times the amplitude of an individual wave times the sine of k, remember k is the wave number now, not spring constant, times x like that. Which looks kind of weird. What happened to the omega t part? Well, if you look at a standing wave pattern, I'm just going to draw part of a standing wave pattern. Something like, something like this, whatever. If I look at a standing wave pattern, like right in here, I know with a string and like with different things, it's different materials, and exactly what's shaking with an electromagnetic wave is a little bit hard to describe, so I'm not going to go into it. It's really just the magnetic field and the electric field shaking off each other. But essentially, I know the string's actually shaking up and down, but there's a maximum amplitude that it goes to. So the position of the string changes with time. One time it's here, next time it's here, then it's down here like this, then it's all the way down to the bottom. So this part here, this describes the shake up and down. This, since it only depends on position, this thing, the amplitude function is really just describing this part. So this part, the maximum up and down, that's really what's being described by this thing. So I can use that as an amplitude function. The other thing to be very careful about with it, and once again, this isn't the most major thing, but the thing is that when they say the maximum amplitude, and this is going to drive people crazy because they'll get the wrong answer in the book, and they'll go, man, I'm getting twice the answer, I'm getting twice the answer, I'm getting twice the correct answer over and over and over again. When they say the maximum amplitude, the maximum amplitude is 2A. So what'll happen, now just to show you, this is just so people don't screw up on the homework. They'll give you a problem, and they'll say, look, the maximum amplitude is going to be, say, 0.004 meters, something like that. And then people look at the amplitude function, and they'll say, oh, okay, my amplitude function says 2 times A, so they go, my amplitude function is 2 times 0.004 meters times the sine of k times x, whatever. No, if they tell you the maximum amplitude is 0.004 meters, that is the 2A. So I really just write it like this. Like I said, people will do that a lot. It'll drive people nuts. When they talk about the maximum amplitude of vibration, the maximum amplitude is this. Okay, it is this amount. Like I said, a little thing, but people miss that. It's not the biggest problem in the world. I can get some other information off of it. Like I said, I've got my amplitude function is this thing. Where would the nodes be? Where are the nodes going to be? And remember, the node occurs when the amplitude is 0, right? I mean, just from the pictures, when you guys did this in lab, you had some sort of string shaking in some pattern, and they said the nodes were where it's fixed, where it's not moving up and down, where the amplitude is essentially 0. So if I asked where are the nodes, and the truth is, for almost all of this stuff, it is better to do it just in terms of drawing pictures. Because what I'm going to do right now, you're going to say, yeah, I knew that from the lab. It was obvious. But I'm trying to work up some math, because where this gets fun in the second half of this chapter is when you're not going for exact constructive or destructive interference, when you're trying to look at places in between. So I just got to deal with the math. So that's kind of why I'm bringing this up. Where are the nodes? Where are these positions going to be? Well, if I look at the amplitude function, I'd say the amplitude function, which is 2A times the sine of kx, the nodes are going to occur when this thing is 0, right? That's where the nodes, right, when the amplitude is 0. And you'd say, well, when is that? Well, 2A is a constant, so that's not going to be 0. So I'm really finding out when this thing is 0 is finding out when the sine of k times x is equal to 0. And you would say, okay, well, the sine of what angle is going to be 0? And if you think in terms of your circle, you start right here, sine of this 0, sine of this 0, sine of this 0, sine of this 0. So you could say that when kx is equal to an integer number of pi, right? Because this would be 0 pi, 1 pi, 2 pi, 3, 4, 5, 6, like that. When k is equal to an integer number of pi, that's when I'm going to get my nodes. When k times x is equal to an integer number of pi, so I go k, I get k times x is equal to an integer number of pi. K is your wave number, so this is 2 pi over the wavelength. Is going to be equal to 2 pi over the wavelength times x is going to be equal to n times pi. So the pi's cancel out like that, and I get the positions where I get my nodes is going to be an integer number of lambda over 2. Which, once again, you knew that beforehand. You said from a node to node, you talked about just looking at the picture. Just looking at the picture, you would say, well, from a node to 2 nodes away, that's less you 1 whole wavelength. So you would say just from the picture, from a node to node is a half a wave apart. That's essentially what this is saying. The position of the nodes is going to be an integer number of half wavelengths. And like I said, it's nothing you didn't know already. I just want to do this because it's going to get more fun. Yeah, let me do that one too. It's going to get more fun. The first half of this chapter, up through resonance with sound, is actually really easy. It's when you get into interference where you're not looking at perfectly constructive and destructive interference, that's when it gets fun. So I got a string. I'm going to say the string is 4 meters long, so the length of the string. And once again, you do this, you do a lot. You could do most of this problem just by looking at pictures. But I'm going to say the length of the string is going to be 4 meters long. I'm going to say it's in its third resonance. It's in its third resonance pattern. I'm going to say it's tied at both ends. That's actually all we've done so far. I'm going to say it's tied at both ends. And I'm going to say the maximum amplitude, A max, is going to be, let's say, 0.008 meters. Okay, that's fine. That's fine. What do I want to ask about that? Yeah. What's the wavelength? What is the wavelength going to be? I don't know that I'm asking these in the right order. What's the wavelength going to be? Where are the nodes? Might be easier to look at. Might be easier to do this looking at where are the nodes first. And let's say the amplitude, which is not going to be at a maximum. This is not at a node, and it's not at an amplitude. It's not at an antinode. Let me say the amplitude at 0.1 meter. I don't know that I asked that right. I should be able to use this idea. I should be able to say, well, the total length of string, which is 4 meters, that should be equal to an integer number, and well, there's going to be 3 nodes, so it's going to be 3 times the wavelength over 2, because this was 3, because I knew there were going to be 3 nodes in it, and I knew that the distance is equal to n times the half a wave, and the whole distance on the whole string is 4 meters, so I can get the wavelength. But I want, God dang it, I didn't want to do it. Whatever, I get the wavelength is going to be something like what does that come out to be? 8/3 of a meter? 8/3 of a meter. That's what one wavelength is going to be. The nodes are going to be at, well, I got a formula for the nodes now. I got a formula for the nodes. I can say the position of the nodes is going to be equal to an integer number of the wavelength. That's 8/3 meters divided by 2. So I'm going to get the nodes are going to be at 1 times. This is 4/3 of a meter. And then I got 2 times 4/3 of a meter. And then the next one is going to be at 3 times 4/3 of a meter. And you could keep going with that, but that's the whole length of the string. So yeah, that's where the nodes are going to be. And actually, I could put in n equals 0. So I could also get the first one at 0. So my nodes are going to be at 0, 4/3, 8/3, and 4 meters. And I was just using that idea. The wavelength, like I said, we already got that. The amplitude of 0.1 meters, probably just going to use this idea. The amplitude, I got an amplitude function for the amplitude, and I want to figure out what the amplitude is. The amplitude is equal to maximum amplitude, which I think I gave you as 0.008 meters times, I think the function is what, the sine of k, which is 2 pi over the wavelength. And yeah, we got the wavelength, that's 8/3 of a meter, times the position x, and I wanted to know where it was at, what, 0.1 meters? At 0.1 meters like that, and if I type that out, that should give me the amplitude at that point, which isn't a maximum, it isn't a minimum, it should be somewhere in between. Do be careful, and once again, just be careful, you know, this in terms of pi, it's going to be in radians. Be careful to change your calculator to radians. So that's going to be 3 times, and I hope you're checking this, because I got 4 times 0.1 equals sine of times 0.008. I think we can type this out. You get the amplitude at that spot is 0.00 186 meters like that. So it's definitely not at a minimum, but it's not at a maximum either. The thing about this is it's always easier to do this stuff just in terms of drawing pictures. And I've done this in labs, so for a lot of people this is going to be repeating stuff that I've talked about, but it's a nice idea. And it's a nice idea because I keep yelling about stuff in terms of strings. A lot of things behave like strings. A lot of this wave description is really useful in a lot of different areas. So what I'd like to do is I'd like to look at resonance with a string that's tied at both ends. So I could do it mathematically like that, but I think it's easier. People will tend to do it using the pictures because it's hard to remember all the different formulas. And once again, once you understand with string, a lot of things work like this. So it's actually very useful. If I have a string, say I got a string that's tied at both ends like this. I'll do something with a loose end in a little bit. If I got a string that's tied at both ends, and you guys saw this in the lab. When you get your first resonance, obviously the ends aren't moving, but I get this really fat antinode in the middle. That would be my first resonance. I would say that's my n equals 1, my first resonance, my first standing wave pattern, my first harmonic. Any one of those terms is fine. And you turn up the frequency, and you notice that when you get the next resonance, you just get another node in there. So it's going to look something like this. And this would be the n equals 2, my second resonance, my second harmonic, my second standing wave pattern. And pretty obviously, each time you go to the next resonance, you just wind up adding another node. So I get something like this for my next pattern. And the drawings get worse and worse as they get more and more complicated. But I got nodes here. This would be my n equals 3, so I got 3 antinodes right there. For my next resonance, it would be 4 antinodes, whatever. Just by drawing this picture, I can find the formulas I need to deal with this thing, because I say, well, in this first case, the length of the string is what? Well, I know, and this is something you really need to know, hopefully I've talked about it enough, that from node to node, is equal to a half a wavelength, always. If you forget that, what a lot of people do, because I can't remember things, I really don't. I go back to drawing pictures all the time. I look at this and I say, well, one wave, if I look at that pattern continuing, oh yeah, from here to here, that's one whole wave. Just think of the wave, you know, the water swinging back and forth like that. And I'd say, well, yeah, from here to here, that's got to be obviously half a wave. And this is a whole wave, so yeah, from node to node is half a wave. It's a nice way to think of node to node is half a wave. So I can say the length of this first thing is going to be equal to, well, that's a half a wave. Now, the wavelength's going to get shorter because as I turn the frequency up, right? If I turn the frequency up, the wavelength gets smaller. In this case, the length stays the same, but now I have two half wavelengths. And then I look here, the length stays the same, but now I've got three half wavelengths. Like I said, it looks weird. The wavelength was getting smaller as the frequency was changing, okay? So I go, you know, how can I use that thing? And I say, I know for any periodic waves, another idea that's really, really, really important, I know it's always true that the frequency times the wavelength is equal to velocity. That's the single most important thing that's in chapter 17, the single most important idea. We'll do other stuff. Honestly, with 17, I think the first half of 17 is pretty easy. I think the second half is not. When we start looking at interference, when you're not at minimums and maximums, it gets to be fun. It's not really bad, but we'll get to it. Anyways, from this idea, I can say that, well, if I solve for the wavelength, I get the wavelength is equal to the velocity over the frequency. I mean, this thing is a perfectly valid statement. I could say, well, in general, the length of the string is going to be an integer number of half waves. And then I could say, well, the wavelength is v over f, so I could say the length of the string is n times v over 2f, just putting v over f in for lambda. And just do a little, you know, multiply both sides by f, divide both sides by L. This is perfectly valid, but they normally write it in terms of frequency. They'll say the frequency is equal to n times v over 2L. What is nice is when I do sound, which I really, really, really hope I'll get to today, when I do sound, you go, man, that's exactly the same thing as the tube open at both ends. It's the exact same thing, and no, it's not, but it's pretty darn close. Anyways, a lot of things can be modeled as strings, which is nice to waste a lot of time on strings, because then the rest of it's easy. Couple things about this. When you get resonance, so tied at both ends, at least let me say fixed. Fixed at both ends, the string resonance is going to be Fn equals n times v over 2L. They'll very commonly write a little subscript. This is multiplier n. It's a little nth subscript. This would be like the nth resonance. If you want to forget that, just leave it out. The other thing to notice about this is I could write this as, and I won't ever do this, but it's n times v over 2L. I can say, well, when n equals 1, my fundamental resonance is going to be v over 2L. What's interesting is if you think about it, your next resonance is going to be at 2 times the fundamental. And the next one is going to be at 3 times the fundamental. The next one is going to be at 4. I mean, if you had your first resonance, and you saw this in lab, it's an important idea. For a string that's tied at both ends, which is going to behave like a tube open at both ends. I'm going to do some screwy stuff with this later on. But if I see that, if I know that this is an open tube, I mean, no, don't even say that. Say I have a tube and I get the first resonance at 12, the next one's 24, the next one's 36, the next one's 48, the next one's 60. Is it an open tube? Yeah, because you'd say an open tube behaves like this, and each resonance is an integer multiple of the first one. Okay, you should have seen that in the lab. That when you had the string that was tied at both ends, your first resonance was something 13, 14, 15, 16, whatever. The next one was about twice that. The third one was 3 times the first, like that. It's a very, very, very nice thing to be able to deal with. Because when I do a string that's open, that's tied at one end and loose at the other, which looks really kind of funny, I won't get this. Now the string, it's not very useful when it's not fixed at one end, but it models something else, which I'll talk about. Try this one. This is just to kind of stop me. I got a I got a string tied, it's fixed right here, it goes over a pulley. So the string here doesn't really shake, it's like fixed at this point, but it goes over a pulley, it's hanging on a mast like this. I'm gonna say the linear density of string is 0.00, let's say 2 kilograms per meter, that's the linear density of string. Let me say I measure this length, let me say this is going to be 6 meters. And I noticed that the fifth resonance, the n equals 5 resonance, so I get 5 bumps on there. N equals 5 occurs when the frequency, which like I could subscript as an F5, is going to be, let's say, 140 hertz. What's this mass going to be? And there's a couple things I do have to be careful about. I'm going to say that I just know ahead of time that this mass is so much bigger than this stuff that I don't have to worry about the mass of the string. If you want to do this problem exactly correctly, it's a fun one, because then you have to worry about the mass of this stuff and the mass of this stuff as far as the tension, because the mass in here, the string actually at rest would actually sag a little bit because of its mass, not very much, but that mass in the string affects the tension. I'm going to pretend, and it does work well. The density, linear density of string is so little that effectively all the tension is due to that mass right there. What is M? So what's kind of weird is I can treat this end as fixed because essentially at some point it'll stop shaking because it comes down here like this. So there's a fixed point here. I can say the resonance is F of 5 is equal to 140 hertz. That's got to be equal to, using that equation, 5 times the velocity of the speed on the string divided by 2 times the L, which is 2 times 6 meters. And I could solve for the velocity on the string, right? And I know how fast the speed on the string is going to be. It's going to be 140 times 12 divided by 5 equals, and I hope you're checking this. I think I get the velocity is like 336 meters per second. That's how fast the vibration is traveling along the string. And then I go back and I say, well, you guys remember, because you used this in the last test, that the velocity is equal to the square of the tension divided by the linear density in the string. It probably, if it comes up again, I'll probably give you this equation. I'm not sure, I don't know, but I give you this equation. I've never asked anybody to derive this thing, so I'd probably give it to you. So I know the velocity, which is 336 meters per second, has to equal the square root of the tension divided by the linear density. The linear density is 0.002 kilograms per meter. If I square both sides, so I square this and then multiply by 0.002, I get, when you work this out, you get something like 225.792, whatever. That's meters squared over seconds squared times kilogram per meter is equal to the tension. If you look at the units, one of the meters cancels out. Kilogram meter per second squared, yeah, that's a newton. So, I mean, obviously, tension was going to come out to be newtons. But let me just round it off. I get 226 newtons is equal to the tension in the string. And then, like I said, I'm going to pretend all the tension is just due to the weight hanging here. I'm going to ignore the mass of the string, which I think is going to be really pretty small compared to mass anyway, so this worked out. I would say the tension due to that weight, it's gotta be equal to m times g. So if I divide 9.8 meters per second squared out of this thing, divided by 9.8 equals, I get that the mass is like 23 kilograms. That's about what mass would be hanging, and yeah, that is so much more than the scrape. Essentially, all the tension was due to that mass right there. Real quick examples.